Okay, it's 10 o'clock. Thanks for joining early, everybody. We appreciate you being here. Today we have Graham Stevens joining us, and we're going to be talking about using statistical Monte Carlo analysis inside HFSS via Optimetrics and Optislang. We appreciate you all joining early, so thanks for coming. On the next slide here, we have a list of our upcoming events. Oh, you know what? I think those are going to be at the end. I wanted to let you know about our upcoming KVA session. So as a reminder, you will get your KVA invite an hour before the session, letting you know what the topic is. However, these are our upcoming 3 topics. Thanks, Graham. So next week is going to be an AutoCAD session. We have Quentin joining us. He's a newer member of our support team, comes to us from Autodesk. He's been teaching AutoCAD for almost 30 years. So be sure to join that session next week. The week after, it's Tiffany Hayden's going to be hosting Assemblies and Autodesk Inventor Planning for Automation. She's an Autodesk Expert Elite, so she has a lot of experience training and a lot of knowledge around Autodesk Inventor. And finally, we're going to have our 2D to 3D transition series. This is part 3. We got some feedback during part 1 that people wanted to see more of a practical analysis of how to actually transition. So this is going to be that session, how to transition, and we're going to show you step by step how to. I'm also going to drop our latest ebook. This has been a really popular ebook, more simulation based, the definitive guide to an electronic assembly design and review. If you're watching on YouTube, that'll be up in the video as well. So check it out. We would love for you to check out all of our resources and let us know how we're doing at the end of the session. There will be a pop-up. You can give us feedback. Let us know what sessions you'd like to see covered, how today's session went. If there's anything that, any other topics you'd like to see covered, we're happy to help. And yeah, if you have any more questions, send us an email. My email is marketing@ketiv.com. We're happy to help. And thank you so much, everybody. I'll let Graham take it away.
All right. Hi, I just wanted to introduce myself briefly. I'm Graham Stevens here, an application engineer here at KETIV. I'm focused on the ANSYS products. I have 25 years of product development, consulting, and simulation experience, and I provide application support for the ANSYS high frequency and low frequency electronic applications, as well as optics and mechanical. Today we're focused on Monte Carlo analysis. I focused the webinar on HFSS, but it really applies throughout AEDT. So we'll be going through the 2 different methods we can do Monte Carlo analysis within the ANSYS universe. The first one is Optimetrics for somewhat of a simplified analysis, and then Optislang, where you can do a lot more options and then consequently get some better results. And when we're talking about Monte Carlo analyses, we're talking about stepping through multiple iterations of a design. And as a result, the computation speed is very critical. So I will be scattering strategies to improve computation speed throughout the presentation today, as well as sort of a summary at the end. And that'll be sort of critical in terms of making these things tractable and possible. So let's sort of start the beginning here. What is a Monte Carlo analysis? As you can sort of see here, we have an input variable, there we go, there's the automation. An input variable here that is normally distributed. And as we start and we do a very few samples, we get sort of a jagged curve or a very flat curve here. And then as we do more and more samples, you can start seeing the normal distribution. And the idea behind the Monte Carlo analysis, of course, is to do some sort of a Six Sigma analysis where we might be having a manufacturing variable that varies with a normal distribution or some other distribution. And we want to find out how is that variability going to affect my analysis results, maybe my antenna performance, maybe something else. And so the idea behind this is to run a whole lot of models look at that with that input variable varying with a normal distribution, and then what's the output, so that we can start seeing the effects of manufacturing variability or other variability on our analysis. And so when we're thinking about AEDT or HFSS and we want to start getting started, the very first thing that we need to have is a parameterized model. And I'm going to switch now to the actual model. And let's make sure this is the right one. Sorry. There we go. Okay. So this model here, I just picked from file open examples. And then within HFSS and antennas, you have a whole host of sample models, and I just picked the helical antenna within here. This model comes where the design properties are already set, where we have the helix radius, the helix feed height, the helix number of turns, and the pitch are all sort of set within the model. And as I vary these variables, the geometry changes, and obviously the performance will also change. And so the first step is to have your model laid out in such a way that you have the underlying geometry, whether it's the helix here, and we do create circle, and we have the helix feed here, call that as variables, where you have geometry that's modifiable and parameterized, and most HFSS users are sort of familiar with this sort of model start. And then once we have that completed, we can start analyzing it through a couple of different methods. So one is in Optimetrics here. If we add a parametric setup, we can take a variable, say the helix feed, and vary it from 3 millimeters to 10 millimeters at 4, 5, 6, 7, 8, and look at the analysis that way. And that's an excellent way to sort of variable by variable check out what's happening. We can also do a sensitivity analysis, which I've done here, which similarly you finger the variables here and say, okay, I want to vary these variables, and I want to do 5 iterations per variable, and I want to tell which of these parameters are actually changing the output. So you might have some that are varying. When you vary a little bit, the output changes a huge amount, and so it's very sensitive to that variable, or you might have others where it's insensitive to that variable. And the idea here of the sensitivity analysis is to figure out which is more important, so that then if you have some of the lesser important variables, you might not include them in the next step, whether it's optimization, which I won't be going over today, or Monte Carlo analysis. So if we want to do a Monte Carlo analysis, we would add a statistical setup here in Optimetrics, and have the same sort of setup calculations, which determine what my output variables are. So I do my output variable, in this case, it might be S11 or antenna gain, and I click on add calculation and done. And then I have a list here of what my output is that I'm interested in. I've got my input variables here. The distribution of the input variables the default is uniform, but you can change it to Gaussian or a normal distribution here, or log normal, or a user-defined distribution. And depending on what distributions you have, you may, this is how you can pick or user define them. We can do an input relative to whether it's Latin hyperacute sampling or not. And then you've got a distribution criteria that are defined here as well in terms of your standard deviation and mean and so forth. So this is sort of defining your input variables and setting up the statistical analysis, and then pressing OK. I'm going to cancel because I don't want to change anything. And then when you run, you just right click on here and analyze. and that will set up and run a Monte Carlo analysis here in HFSS. A separate way to set up and run a Monte Carlo analysis is using Optislang. And HFSS is attempting to add this Optislang setup here. But I've found that actually the setup here it's still not quite ready for prime time, and it's easier to just go to Optislang directly for these setups. If you go into Optislang here, we'll just switch to Optislang. Optislang, to set up the analysis, you want to click on this solver wizard up here and drop it in, and then set your settings here relative to which variables it's pulling and so forth. Sorry, it's taking a while to open here. You can sort of take a look here. But the easiest way to do this setup is to click on this solver wizard and have that come up. Come on, where is it? There we go, okay. And so within the solver wizard, you have the parameters that you set up, criteria if you're looking to do an optimization of some sort, and then your other settings here, which you don't usually need to worry about these too much. And typically within the solver wizard, you'll also set up this link between AEDT and Optislang, where you have an AEDT model that's indicated here. This is where the model is, and then what the outputs are. And typically when we have this model, so I have this helical antenna for optimization for Optislang here. It's important to reduce the model's computation size and length as much as possible. So we might have sweeps where we only have 20 points in the sweep rather than the usual 500 or 1,000. Or we might eliminate the sweep altogether and just disable the sweep, depending on what my outputs are. I might change the analysis settings here to first order basis functions, which solve a little tiny bit faster than mixed order. I might use the direct solver, the iterative solver, again, depending on which one's faster. So I might do save fields and save radiated fields only to reduce the amount of disk space that each analysis takes. So there's a number of different steps you can take in here. And as you're setting up your analysis in terms of your solver, maybe you want to use the planar solver instead of the FEM solver can be faster. A number of tips and tricks that I've done in other videos to simplify your analysis and simplify the geometry that's here and how it's been done, so that we get the time for an analysis to be as small as possible. Typically for the HFSS model that you're feeding into Optislang, you also want to make sure that there are no Optimetrics analyses here, because of course those would force you to run parametrization of 10 times or 20 times for each run that Optislang is doing, and we don't want that. And the other preparation item that you should do is for the results. Normally you would create a modal solution report and do a rectangular plot for your, say, S parameter. But in this case, I've eliminated all of those graphic reports and gone in favor of a data table here. And so I've set up a data table for my S parameter 1,1 and for my gain for this antenna. And then you also want to right click on each of those tables and export them. And that sets up an Excel spreadsheet right in the same directory that this model is in, which Optislang then uses as sort of the input for its analysis. And when you go through the Optislang setup, it will create some routines that automatically create those tables and grab them for these analyses. So that's the setup of a reduced, not a reduced set, but just a reduced computation model. You also want to take a look at your simulation and your HPC options here, and think about how many cores am I going to be using. Think about the number of variations you're distributing as well, in terms of parallelization, relative to how many licenses you have and so forth, and make sure these settings are also set. Once all that's done, you then hop back to Optislang, and as I said, go through the solver wizard and initially set this up. What will happen is you'll come in and you'll see these variables here. Typically, you'll right-click on them and use as internal variable to finger those outputs and say, yes, this is what I want to use. And then if you go to the variable tab here, typically those table variables, you'll notice, are in this format of their real XY data 1-to-1. And so it's an XY table format. And when we're running in Optislang, we want to have our variables be a real or a single valued variable. And so I've added some variables here called max gain and min S11, and just grabbed the mean off of that table for each one of these, and then taken these variables and plunked them over here in the response side, so that we now have our input variables of the 4 variables that were in the original model, and now our output variables here all set up. And then on the run side, we have again our maximum number of iterations in parallel. And so that's how this sub-block is set up. Once we have our solver wizard set up, where we have a block and we've done a solve, then we can set up a sensitivity analysis by taking the sensitivity wizard, dropping it on top of this block, and then it will pop up a sensitivity analysis based on that. And this is where we start setting the settings for the sensitivity analysis. So we say Latin hyperacute sampling and number of samples. We look at the parameterization. In this case, I did discrete by variable for these helix terms, 7 through 10, but not any partials. Set up a criteria if we have an objective. In this case, I want to maximize my gain, and so forth. And similarly, if we have an optimization, once we've identified which variables are important, and we say eliminate consideration of the variables that aren't important, we can then take this optimization wizard, drop it onto the sensitivity, so it uses the results of the sensitivity as the basis for the optimization, and we run an optimization analysis. And then similarly, and most importantly on the Monte Carlo side, we take a robustness wizard and drop it on top of the optimization, where it will then take the resultant optimized iteration from this analysis here and use that as a robustness, where in this case, we now have our parameters, and instead of our parameters varying by continuous variables, we now change them to stochastic variables here, where we can then indicate what the distribution is and how we want those variables to vary. And one advantage of Optislang, of course, is the types of distributions that are available here are, let's see if we can widen this up so I can see a little better. So our, far more distribution available as sort of a standard option. Yeah, pretty much you just find just about any distribution you might want in here. This allows us to set these distributions, and then the nominal design that we're starting from, again, criteria that we try to maximize our gain. And then we set our dynamic sampling here, and this can be a plain Monte Carlo, Latin hypercube, advanced Latin hypercube, etc. In general, Optislang is trying to reduce the total number of runs, and so you generally want to sort of go with the defaults here, and it tends to shift you away from just plain Monte Carlo, which is just at random, and try and get some more logic and reduce the total number of samples needed to get results. And then we get our result designs here. So that's a quick broad brush stroke through the setup of both Optislang and Optimetrics. And so we just went through that. And now I want to sort of take another step back here, and let's think a little bit more about our Monte Carlo analyses and when we set these up and how we want to do this. So one thing that's really important on a Monte Carlo analysis is those distributions. If I'm assuming a normal distribution, that's an assumption. And the question is that correct? Or is it skewed? Like, is my manufacturing variable actually plus or minus 5 thousandths or 5 mils or whatever dimension it is? Or is it actually plus 0 minus 1 or plus 5 minus 0 or whatever? So it could be skewed, it could be not, but you want to really try and understand those distributions and make sure they're correct in terms of ensuring Six Sigma validation of your Monte Carlo analysis. And some other options, of course, if you don't know those distributions really well, you can kind of assume a worst case scenario. If it's a uniform distribution anywhere between value A to B, you could do some sort of a triangular distribution where it's, the minimum is something, the maximum is something else, and the average is somewhere else. In this case, it's skewed, but you could have a triangular distribution that's sort of right in the middle. Or you can just assume that it's normally distributed. So you want to make sure that you maybe use uniform distributions or kind of rough triangle distributions if you really don't know what the variable is, or the variable's statistical distribution is. And if you do know that, you want to kind of specify it precisely. Because if you've got the wrong inputs, of course, you're going to get the wrong outputs on the other end. And then with regards to sensitivity analysis, Optislang offers something called a meta-model of optimal prognosis, where instead of sort of a standard one-dimensional polynomial regression or a gradient-based approach, which Optimetrics has, Optislang has much more sophisticated models. And this meta-model of optimal prognosis can handle nonlinear dependencies, nonlinear interactions. It has a prognosis quality as an error measure to see how well does the internal meta-model conform to the actual reality, and you can take a look at that to see if the predictions are good or not. If they're not, you can use what's known as run models, where it just runs the model and runs the HFSS model. But if the meta model of optimal prognosis is highly correlated, then you can use that, and it's basically a polynomial-esque approximation of the results from the HFSS model, which then runs a heck of a lot faster. And so you can speed up your analysis by using this meta model if the meta model applies or has good correlation with what you're doing. And then similarly on the optimization side, the optimizers within Optimetrics are 10 or 20 years old, and then they kind of stopped at the gradient-based optimization and or the response surface methods and a tiny bit random genetic evolutionary algorithm. But from 20 years ago to today, there's been more progress in this kind of optimization in terms of optimization methods. And Optislang is the best tool for this kind of work. And so you have more options in terms of the downhill simplex method, particle swarm, evolutionary and genetic algorithms that are more up to date. And so you'll get a better optimization result when you use Optislang, but you may want to sort of, but if you're looking for just something simple, down and dirty, then perhaps Optimetrics might make sense, especially on the gradient-based side. So just keep in mind the differences here in terms of optimization methodologies. And similarly, for variance-based robustness evaluation, which is what we're thinking about in terms of Monte Carlo analyses, there are different methods of doing these kinds of analyses as well. We've been kind of focused on Monte Carlo, but you can also take a look at these other ones: first order linearization, polynomial chaos expansion, global response surface, etc. And all of these are part of the Optislang suite as well, and maybe might be a better choice in some manners at sometimes than Monte Carlo. And as we go to Six Sigma reliability in particular, when you have Six Sigma reliability, you really want to run analyses around the dominant failure regions, and you have to do that with a sufficient accuracy. And so typically for Monte Carlo, you'll get into large amounts of run, tens of thousands of runs or millions of runs to get to 5 or 6 sigma or 3 or 5 sigma here. And Optislang has some directional sampling, some of these other methods in terms of qualified reliability methods that'll reduce the total number of runs to get equivalent results relative to these dominant failure regions, and really get a better sense of whether your design is going to fail given XYZ variability. I should also mention too that you can change the material properties within HFSS as well, create a project variable, and then vary that material variable. And a lot of times in simulations, relative to how well the simulation corresponds to reality, we sometimes don't know the material properties as well as we need to. And so that's another key area of sort of double checking your simulation results to see, is it within the measured realm given XYZ variability of these parameters, dielectric material properties, etc. And then I also recommend that all of you, if you're thinking about this kind of optimization work, within the ANSYS Learning Hub, there's a course on Optislang that goes through kind of robust design optimization. And that's where most of this material came from. And there's gobs of extra information underneath some of these slides, which is very useful to think about as you're thinking about these analyses. They have a workflow here relative to, you want to do a sensitivity analysis so that you throw out the variables that you don't, that aren't important, then you optimize to those. But the optimization, when you get to a variance-based robustness evaluation or Monte Carlo analysis, you might need to expand the total number of variables because you were optimizing based on this subset of variables that you needed to focus on in terms of what was important. But then there might be other things that are important, whether it's loading conditions or material variability or different configurations that might cause you variance in the field, and you need to take that into account for your Monte Carlo analysis. So you may have to kind of go back and look at some of these, redefine some of your input variables relative to your robustness analysis to make sure you really capture everything that can possibly happen, so that you get a finalized Monte Carlo distribution at the end that really takes into account all the variables. Yeah, and so if we switch back to our models now, oops, sorry, let me grab the right one. Okay, so this is the model that I was using for just Optimetrics. Within here, under sensitivity analysis, if we right-click and view analysis result, you can see for each of the variables here, it ran a number of models to try and take a look at, well, how did peak gain vary with the number of turns? And so we can see here peak gain varying with the number of turns. Here's how the pitch varied. Here's how the feed varied. Here's how the helix radius varied. And so this allows you to sort of get a feel for which ones are important, and we can do the same thing on the S11. And so this is sort of the output for this kind of analysis. And this profile sort of shows you, well, how many models did it run and what were my input variables for each of those runs. So that's on the sensitivity side, what the results look like. And on the statistical setup, we again right-click here and view analysis result. We can now look at S11 or the peak gain in terms of you can sort of see here, I just did like 50 runs instead of thousands, just to make it a shorter runtime, but we can sort of see the number of outcomes distributed here and what our output S11 is and our peak gain. And yeah, so that's the analysis here. You can also, of course, within these runs, do a result where you pick the results from those sensitivity runs and output those as well. I'm not going to go into how to do those sorts of graphs, but you can do additional graphs that sort of grab all the runs that were done in terms of the families and results. And then in the Optislang arena, when we start looking at some of these post-processing runs, if we look at, say, the that's not good. Sorry about that. It's interesting. Get this one. This post-processing does take a while to come up. Let's see if there we go. Okay, so this is on the optimization side. Typically, when we're looking at this, okay, still thinking and coming up with my other thing. I turned it on to open. Sorry, it's going to take a minute again. Yeah. Okay, so on the optimization side, if we view toolbars visuals here, we have, you can sort of see how the output here, this is the optimization of the what's known as goal function. So we were trying to get gain to be as high as possible. And so it was sort of striving and doing another variation, then getting to this one, and it kind of found the best option was this design 55 here. And some of the other very interesting analyses or data mining that this allows you to do, let's see, is look at a spider plot here where you can look at all of the design iterations, and you can play with these parameters as well. And then the other one is this parallel coordinates plot is very interesting, where I have my gain function. I'm looking for max gain, and I can just vary some of the input, say helix pitch, and say, okay, I'm going to vary it from this to that, and now I can look at all of the different iterations that satisfied that to get to this maximum gain. Or I can say, I'm going to go my maximum gain to here, and I want to cut off all the rest of them. And so then I look at, well, what parameters got me to that maximum gain. So this parallel coordinates plot is very useful in terms of understanding and comprehending the results. And of course, we can also look at the same kind of XY plots that we were previously as well. And similarly, on the robustness side, we can have this, oops, what happened? My histogram. We look at the, sorry. data. I'm not sure what's happened in this histogram setting. Give me a second here. Anyway, you can see how the histogram, there we go. So this is the histogram for the helic pitch. We can change that to the radius, etc., and get a better feel for how did the outputs here correspond to the inputs. Of course, our input distributions here were normal, so the outputs look pretty normal as well. And there's a lot of, again, other views here in terms of response surfaces. Let's see, let's get a 3D response surface. 3D plot here is very useful to sort of look at, okay, for my helix, for these two variables, helix feed and helix radii, how did my, how do my results vary with those? And you can sort of see how, if I want a high gain, I want to have my helix antenna, helix feed to be higher than 0.65 type of thing. So we get some really interesting results and views as we look at how different variables interact, in addition to just the one by one. So that's the results that I wanted to show you here. And if we go back to the presentation along tips and tricks, I just wanted to kind of remind you of a few things here. So because the model will be running repeatedly over and over 500 times, 1,000 times for Monte Carlo analysis or for this type of analysis, this is the time where it is worth spending a lot of extra setup time to do everything you can to just reduce the simulation time. So that could be simplify the geometry, as I showed earlier, eliminate the extraneous results, reduce the frequency, sweep breadth, maybe only have one frequency point as opposed to a whole host of them. Don't save the fields or save only radiated fields, change to first order basis functions. You can also widen the accuracy results. So instead of 0.02, maybe go to 0.05, again, depending on this balance of how accurate do I need to be versus what I'm looking for. And that reduces the number of passes to the bare minimum, which of course impacts your total time. And then optimize your solver usage. So you could use the planar solver, or you could do composite excitations, or a number of other tips and tricks there. Please see this strategies to speed up your mechanical and electronics ANSYS simulations, which goes over a bunch of those different topics. And then when we're doing the optimization, doing the Monte Carlo, we want to use sensitivity analysis to eliminate the non-important variables so that we're not examining those anymore. And then use uniform triangular Gaussian distributions where the input stochastics are not really well known. And then once optimized, you might need to broaden your input variables for consideration for reliability runs in terms of just capturing some of those other extraneous parameters or other variables that you might not have thought about initially in the design. And with that, I will pause for questions. If there are questions in the chat. Okay, so lacking any questions, I'll come to this final slide here. ANSYS, HFSS, Optimetrics, and Optislang can be used to run Monte Carlo analysis runs to account for manufacturing variability. We heartily recommend Optislang for this task as opposed to Optimetrics, but you can use Optimetrics as well. And please do email support@ketiv.com if you're looking to get access to the ANSYS Learning Hub. If you have questions in your setups in terms of running Optislang or running Optimetrics this way. Within the Learning Hub, there's some links here to both the HFSS Getting Started. Optimetrics within HFSS is in the Getting Started course, and that's here. There's a Optislang Getting Started Learning Room here as well, and then an Optislang Robust Design Optimization course that we recommend here as well. And even if you're planning on using Optimetrics, it's worth going through the Optislang course so that you can get a feel for some of the theory and some of the new developments that have happened relative to optimization theory and practice, even if you end up using Optimetrics. Yeah, heartily recommend diving into this material if you're going into this space. And then, of course, some other resources relative to getting this work done. ANSYS has a how-to YouTube channel. KETIV has more YouTube videos as well. As I was mentioning before, there are some webinars here at ANSYS, Resource Center for Webinars. And then, of course, the innovation space within ANSYS is free courses as well, which covers other subtopics and setup. Also wanted to make you aware that KETIV also does simulation services in these three areas: mechanical, fluids, and electronics. And please keep us in mind if you're looking for help. We do training in this area as well, and kind of you do it 100% or we do it 100% and anything in between, or we do it 100% first and then train you so that you get to do it and then you're off the training wheels and go. We do this kind of consulting work in relation to training, basically to get you up to speed and get you going. So just wanted you to be aware of that capability and help that's out there. And with that, I think I am finished.
Thank you so much, Graham, and thank you to everybody for joining. You can email us marketing@ketiv.com or support@ketiv.com if you have further questions. We will see you all at next week's KVA. Thanks, everybody.
Take care, guys.